Welcome back, guys, to part 2. So in this part, what we're going to be going over is how to calculate the surface. So to do that, what we need to do is, just like I mentioned in the last part, is we're going to be using the normal and binormal vectors. So what's going to happen is I'm just going to draw another ellipses here. The center's about here. Our binormal is going to be up here, where b is just a scalar representing the radius. And the same thing here, where a is just a scalar, because remember, n and b are vectors, but they're also unit vectors, so their magnitude is just 1. So what you might notice is these look very similar to like approximation vectors. So when you add them together, you'll get a point like, say, right here. But what we want to do is we want to get the entire circle, or ellipses. So to do that, we got to do something called a rotation matrix, where usually in a vector you have is just like on an xy plane here. Where this is, say, vector v. It can be approximated using I and j vectors, or I and j unit vectors. So, since they're unit vectors, their magnitude is 1. So when we go to plot it out in like a matrix form, stop doing that. So for example, our first column here is our I. So the first row represents our x component, y component. First column is I, second column is j. 0, 1. And then we have another vector here, or matrix, that just contains our constants, saying since this is 1, the C1 is the magnitude, or the length of the vector. But, say for example, we wanted to rotate this 30 degrees up to here, or at some angle theta, and instead of just trying to find the new one, what we can do is rotate this one. So to do that, what we gotta do is we're essentially shifting the I and j unit vectors. So what happens is our j is shifted this way. So now this becomes the sine of theta and this now is the cosine of theta. And same deal over here, where this is going to get rotated by theta, sine of theta, cosine of theta. So what ends up happening is, instead of having the 1, 0, 0, 1, the rotation matrix now becomes, or the unit matrix, I'll just call it, now becomes this. So cosine of theta, and then sine theta, Now notice that this sine of theta is going in the negative x direction, so that makes it negative. And then cosine of theta, this part right here, is in the positive y, so it's still positive. And then we're still multiplying by that C1, C2. So if we go back to our collab, we can sort of like view that through using Plotly and then JMP again. So to start, what we want to do is let's set the number of thetas we want to calculate or pass through first. So let's set that like at a 32. So if we do thetas, len space, and then do 0 to 2 pi, and then let's do n thetas. So what that's doing is just having an evenly spaced data points from 0 to 2 pi that we can use for Plotly, JMP, whatever we need to do. So after that, what we can do is we need to make a rotation matrix function. Okay. Do drop mount t theta. So with that, what we'll do is just make a JMP array, and then JMP.cosine of theta, JMP.sine of theta, JMP.sine of theta, and then JMP.cosine theta. And then what we are going to do is reshape that as a 2 by 2. So now what that's doing is that's making our rotation matrix, which we can then apply to a vector. So for example, what we can do is make a initial vector v0, jmp.array, at, say, started at like 1, 0. We're going to make those 2 rows and 1 column, just because how the vectors are set up here, where C1 and C2 is in a column and not a row. So now that we got that, what we can do is we can make another figure. So we're remaking that figure. And then what we can do is make a variable res and set that equal to rotation matrix thetas. Multiply that against v0. What is that doing? Oh, okay. So what's happening here is It's designed to take in a single value, theta, and give out a matrix of 2 by 2. So if I let me try something. Vectorize. Sure. Now, if I look at res dot shape, see what that did. Alright, so we have 32 thetas. We have 2. So 32 thetas. We got 2 rows and 1 column. So, okay. I'm going to look at the transpose of that. Okay. So for each theta, it has 2 rows, 1 column, so it has an x and y in each. So if I look at, say, the first theta, it gives us a 1 and a 0. Do the transpose of that. Yeah. Okay. So what's going to happen here? Let me think of a good way to get from here. Okay. That is funky, but what's a better way to do this? Alright, but just to show you what's going on now is, so for t in res, let's remember res dot shape. Alright, so it's going to go through these 32 thetas. It's going to give us 2 rows. Try something else. Let's see what shape that gives us. Okay. Alright. So, now if we do it like this, there we go. So what happens here now is our first one is all our x's, our second row is all our y's. And we don't need that. Thank God. Add trace. Go dot scatter. X equals 0, y equals res 1. as you can see, we do get a little circle, but it is extended because the ranges are weird. So, if I go here, go fig that update layout. There we go. You can see it's a lot, much better, more circular action. And that's using our rotation matrix, where we have 1, 0 here, go up whatever this amount of degrees is, and then we just use our rotation matrix to get all the way around. So with that, what we can now do is we can make a surface function to where we can do is we're just going to get surface points. So we need a time and we need a theta. The reason we need that theta is what happened is that t is going to give us the position of the helix. So the t will give us this point, like say here. The theta is going to say, okay, at this point here, rotate however many to get this point on the, and that's the surface point. So if we go back down here, and so we got the surface. Then just like I was explaining right here, a reminder, the binormal is just the cross product of n and t. Now keep in mind we have to follow the right hand rule, so the tangent should actually go out in front of the normal. Otherwise what's going to happen is the binormal is going to point down, and we don't want to mess with negatives. Or at least I don't want to. So that's why we're going to have tangent cross product n. So first thing we got to do is we got to get our n, which thanks to our Fresnet right here, we have a function for that now. Variable sometime t, and then we also got tangent at some time t, and then our binormal is going to be jmt cross t n. So now we got our binormal, and then what we got to do from here is where we have to worry about that rotation matrix. What I'm going to do is I'm going to set b equal to our rotation matrix, or the function, theta. I'm going to do some matrix multiplication. Right. Here. To get it into the shape we want it. So, what happens now is we can return the surface point, which is going to be v0 multiplied by a times our normal vector plus 1 times our e times our tangent vector. And then, so as you can see, there's a little markings underneath because a and b are not defined yet. I'm going to go back up here, we defined r and mz. I'm going to just add it here so they're all in one spot. So a will do like 1, and then b we will do 0.5. run that. Trying to close that again. So you can see that red line's gone, so now it's defined in a global scope, so that's where it's picking that up. So now, we got that. So, now, let's do the number of times. Let's set that equal to, just to start out, let's do like 5. So jmp.lin space 0 to 6 pi. Oh, excuse me. And then what happens is we try to do surf t theta. T's and the thetas. What's going to happen here? Okay, so what's happening here is it's trying to pass all the t's in at once, but that's not what we wanted it to do. So if we go back up here, this is where JMP vectorize comes back in. So if we try doing that, see what that does. Let's try add this, see if that works. Okay. So I have to actually pass in the signature. It's going to look a little ugly, but it works. Scalar, scalar, and then our vector down here is going to return 3 numbers. So that's going to be a 3. So now if I try that, alright. So what happens here is, let me just get the shape easier to explain it that way. So nt is our very first number here is our 5. So for each nt, it's going to be 32 rows representing the thetas, and then 3 columns representing the x, the y, and the z. So that's where those numbers are coming from. So, what we'll do here is just make that a variable, surf points, then force, how do I want to do this? So for surf points, let me think about this real quick. So we want to iterate through each of the t's, because that's going to give us our position. And then that position, we need to get those 32 rows, or we're going to want to get the transpose of those to make that easier, I believe. So t index in range in t. What I want to do is let me make another figure. And then I'm missing anything here. Okay, so I want to do points equal to surf points. T T index is the very first one. Got all of those. Just like I mentioned before, I want the transpose of that. The reason why is when I go down here, surf points. So I grab the very first one. What I'm going to do now, run that. Doing wrong here. Oh, that's why. Okay, so yeah, as I was saying, so if I look at just the first T index, so right now it has 32 rows, but what I want to do is I want to make that 3 rows corresponding to X, Y, and Z. So that's why the transpose is there. So if I do fig.add_trace, fig.scatter 3D, because we're back on the 3D plane, x equals 0.0, y equals 0.1, z equals 0.2. Look at that. So, you can see it's a funky looking shape. You just go up here on a node equals lines. Yeah. So, right now it looks like a freaky disco ball. And the reason for that, I believe, go back up here, yep. So, the reason it's doing that is all of this is relative to the 0. To the center of that, wherever that point is. So to do that, we have to provide the center using our helix. So helix time, and then RMZ just from the global scope. Do all that again. Right, so as you can see, now it's looking a lot more like a coil shape that way. So, just to make it a little bit easier to see, we've got add trace. If I do that, you can see getting ellipses on the actual points. If I run that. Alright, so 1 second. I just get rid of this for a second. Okay, yeah. So I do it like that. I screw up something in here? Not time. Oh, that's why. So instead of doing the smart thing, putting a B, I put a T. So that's why they were all acting weird and essentially making little circles along the curve. So if I try doing it now, yeah. So it does look a little elongated along the Z, which I don't understand how that's happening. But could just be a whole scaling thing. We got 2, -2 here, 0 to 10 there. But as you can see, we have our ellipses here. The only thing we have to do now is probably like bump that up to like 20. Yeah. So now we have our ellipses. All we have to do now is connect them. The one thing I'm not liking is this legend. So let me go up here to our default layout and get rid of that legend. Alright. Got rid of that legend. And now we got this. So all I gotta do from here is we just need to get our ellipses connected. And preferably the same color. So here, just going to the same thing, line is dipped, color, and let's just make it all white. So FF. So if I run this, we got a comma. I run this, yeah, so all the ellipses are white now. So now, instead of doing t index, what we can do is use our theta index. So points equals points. Index. Then same deal, let's take the transpose of that. Then we're going to add that trace. Lines. Yeah, so it's a little bit of a cruddy simulation or representation just because of how rigid it looks. So if we go up here and then update our NT to be like, say, 100, you see it's a lot more helix. And so that right there is our surface. That is for our part 2. So in the next part, we'll be going over part 3, where we're going to vectorize the surface. Or, well, might have already done part 3. Might have jumped the gun a little bit. But, yeah, so by vectorizing this jmp.vectorize, where is it? Right here. passing this signature saying t is a scalar, theta is a scalar. We're essentially drawing a grid. So if we go over here, what I mean by grid is we have our t's going down like this column, and then our thetas going across, and then so for every t, we want calculations for all of these. And then at this t, we want calculations for all of these. Or vice versa, at this theta, we want calculations for all t's. All t's, right here. And then so on and so forth for every t. So that's what this vectorize is essentially doing. So, that's where that came from. That's what the vectorize in the homework is talking about here. And then, this plot, what our part 3 is talking about. Where by going through the t indexes we can draw the ellipses, but by going through the theta indexes we can draw the connections through them. And then by increasing the nt's and the n thetas enough, we get this very helix looking shape with an ellipses going throughout it. So in the next part, what we're going to be talking about instead is, if this thing does not stop, I swear on Jesus's baby self. Anyways, going on to part 4, calculate the surface by summing the magnitude of the cross product of the vectors to find the discrete parallelograms, where we'll go more in depth in just a bit, but just give you a preview. Cross product just gives you a vector in the third dimension. But if you take the magnitude of that, what you get is the area between the two vectors. So between vector A and vector B, you get this area. And then we're going to be using that to find the entire surface area of this entire shape.